go on with the next session. Salvo Vitale will be telling us about how we can do cosmology with gravitational waves.
Thank you. I hope you can hear me. Yeah, I can hear myself. So, all right. First of all, let me thank the organizer for inviting me. I'm very happy to be back in Korea. I had a good time in Seoul before coming here. I had a lot of good food. In fact, I could have given a whole half-an-hour talk with pictures of food I ate, but yesterday I promised you I would talk about gravitational waves instead, and I cannot take that back. All right, so as I mentioned yesterday, it is possible to measure cosmological parameters, in particular these days, H0 with gravitational waves. And okay, the slides are cut, which is not going to be very easy to go through then. Maybe we can switch to the 4/3 version. I came prepared, so I have a 69 and a 4/3 version. Can you switch the other file? This one, it's cut on that side. Thank you. Yeah? The file which has 4.3 on the name? You should have it. Maybe still on the hard disk. Yeah, it works here. It's just got there. Yeah, this one, 4.3, yeah. Let's see if that works better. Yeah, this one. Okay, let's see if this one is any better. Yeah, it works. Kind of works. Okay, I'm not sure what's happening. I'll try to remember what I wrote. Okay, so let me give a bit of background, although it's not really necessary after yesterday's session. I'll be very quick. So we do a way of measuring cosmological parameters. We have actually a redundant number of ways, and you heard a lot of very good talks yesterday about that. And unfortunately, while overall the big picture is probably clear, these methods, or some of these methods, disagree, in particular on the value of the Hubble constant in a now significant way. And so when I look at this from my point of view, someone that works with gravitational waves, and I think about measuring H0, really what I want and what I need is to have a source for which I can measure at the same time the redshift and the luminosity distance. And now the nice thing about gravitational waves is that they do give you the luminosity distance to a source directly without any modeling, basically. But so before I go into details, let me very quickly show, very slowly apparently, what kind of sources we expect we can get from LIGO. Chun-Li mentioned something about that before. We have transients and persistent sources. In the transients, we have compact binaries and bursts, like supernovae, blowing up. And on the persistent side, we have pulsars, as long as they are not perfectly spherical. And the stochastic background, which can be of two types, really. The one that was hinted at a few days ago, which is the stochastic background from inflation, which is going to be very challenging for ground-based detectors to measure, or the stochastic background coming from the sum of all the unresolved sources. And today, I'm only going to focus on compact binaries. You have seen this video already, although at a different frame rate earlier. All right, let me see if I can change slide. I like to start with this plot. So a few years ago, I was talking with Paul Schechter, that probably some of you know, actually during my job talk at MIT. And Paul drew this cartoon on this plot on the blackboard, and he told me, you know what it is? Yes. And he told me, if I look at this plot by all of any feature, the deep to trough ratio, how many maximum you have, and so on and so forth, I can tell something about the universe. Then he told me, now I want you to plot a gravitational wave and do the same thing. From each of the features in the gravitational wave, tell me what you learn. Okay, which I thought it was actually very interesting and very useful. So I'll try to do it today, although a shorter version because of time. This is a gravitational wave coming from a compact binary, two black holes. You have seen this before. In particular, this refers to the first gravitational wave. So for example, looking at this waveform, from the length, so how long it was in the LIGO band, I can tell you something about the masses. This is less than a second. It's way less than a second. So I can tell you that these are two black holes. They're non-neutron stars, for example. From the fact that the amplitude is monotonically increasing, I can tell you that either there were no spins or the spins were aligned with the orbital angular momentum. And from the phase evolution, I can tell you what the total mass is, or the chirp mass, rather. But today, more important, what I want to focus, it's the overall amplitude. From the overall amplitude, I can kind of tell you how far the system was. And the reason is that the amplitude of a gravitational wave, which, as you know, come in two polarization, we have seen this a few days ago in plus and cross. Well, in both polarization, the amplitude of the signal goes like 1 over the luminosity distance. Okay, so by measuring the amplitude, which is measuring the signal-to-noise ratio, I can tell you something about the distance. There is a slight complication here, which will become important later. In both polarization, the distance is not by itself. It always comes in a combination with the inclination angle, which is the angle between the angular momentum and the line of sight. Okay, so we're looking at the system from here. And the reason why this happens physically is actually pretty easy to understand. If you have a compact binary, the energy, the gravitational energy, is not radiated isotropically. More energy goes along plus and minus L, and less energy goes along the plane of the orbit. So once you fix the signal-to-noise ratio in your detector, you can obtain that SNR in two ways. By a source which is farther away but oriented with L coming at you, or a source which is closer but more tilted. That's the physical reason why we have this correlation or rather degeneracy. All right, so that's to give you the idea of how we measure the luminosity distance and physically, but that's half of the problem. We need the redshift. How do we get the redshift? The gravitational wave directly will not tell you, will not give you the redshift. And over the last decades, really, starting from '86, people have started thinking about ways, smart ways actually, of getting the redshift in absence or, of direct measurements from the gravitational wave. And probably the first thing that comes to mind is that if by any chance my compact binary also produces an electromagnetic counterpart, maybe I can localize the event very precisely. I see the galaxy, and we have heard this today in the first talk, and that gives me the redshift. And that's the obvious thing to do. It's important to know that it's not the only way you can do it. There are other ways in which you can do it even in absence of an electromagnetic counterpart. For example, if you know the equation of state of a neutron star, then with gravitational wave data only, you can get both distance and redshift. I won't time to go into details today. You can ask me at the lunch or coffee break. And this is also true if you get the post-merger signal. Another very nice idea is that if you assume that all the neutron stars in the universe come from the same mass function, say a Gaussian, then if you know the functional form of the underlying population, you can get the redshift in a statistical way. That's very tricky. Again, it takes half an hour to explain it more carefully. Ask me later if you want. And even if you don't get any electromagnetic counterpart, another thing that you can do, if you have a galaxy catalog that covers the error region associated with your event, is that you can get your sky map, actually as a volume, really, because we have the distance and array and deck. You can just take all the galaxies which are consistent or compatible with your volume, and you follow up them one by one. You assume that each of them in turn is the real host. Each of them will give you a redshift. All of them but one will be the wrong redshift, of course. You can convert redshift to Hubble constant. I have a plot which I can show later, maybe. And of course, it will be horrible the first time because you have gazillions of galaxies and all of them but one are wrong. But if you do this over and over, as you get more and more events, the true host will always contribute to the same bin in the H0 posterior, while everything else will act as a noise. So eventually, you should still win. It just will take a while. All right, and today, so for reason of time, I will not cover at all these methods in the middle. I will only say something about the first and the last. So the other thing I want to say is that this plot doesn't work. There is an issue with the plot. Right. I can tell you what this was supposed to show. It was supposed to show you the horizon on which you can see sources at different masses as a function of their true mass, okay, for different instruments. I don't know, Chair, can I try to do something about it? Because it's actually better if you look at the plot. Because I think it shows up in there. The plot is missing No, it doesn't show up here either. Okay. No, it's not okay. Like, meaning it's okay. It's not working really. Can I? Let's see. I can try to provide a PDF if it's better.
In the other version, would it show up?
I don't know. Can you try to switch to the other version, please? The other file. Let's see if you have this one here. No. So it must be a version of PowerPoint issue. I can quickly convert to PDF. And sorry, people, but on the other end, we think we have half an hour empty after the second talk. So I will not lie. Okay, give me a second. Sorry. Or I can connect my own laptop, yeah, if that's possible. Do we have a Mac to VGA dongle? Yeah, we do. Okay, perfect. Let me just turn the Wi-Fi on in case I have any like private LIGO email that shows up. Okay. Yeah, exactly. You know, you are joking, but I have to be careful with this stuff. It happened to people that they were giving talk, and you know, you have the pop-up of a new email with something that people were not supposed to see. Okay. So let me go here. Okay, try that, please. Okay, let's see if I can put it big. Okay, that works. And I cannot change slides, though I need this one. All right, let's try again, this time with actual data on the plot. I lost the pointer. Okay, so this plot is showing for different total mass in the source frame. So this would be a binary neutron star, and this would be something like the first black hole binary we detected. How far you can see them in the universe in redshift. As you know, a function of which detectors you're using. Here you're seeing a few things. One of them, you know, it's LIGO, advanced LIGO. Design sensitivity. The others are projected upgrades or future instruments. And here there is a very rough timeline. You should not take this too seriously at this stage. But the point I want to make with this plot is that even once advanced LIGO is at design sensitivity in 2 or 3 years, we will see neutron stars binary at most at z of 0.1-ish. Okay. On the other hand, when we have this third generation or these future detectors, we'll actually see, or we can see neutron star binaries to redshift of order of unity. So it will be, of course, much more interesting if you want to go after dark energy equational state and such. All right, so I don't probably need to spend a lot of time on tell you how the ideas of the methods work. We have seen these cartoons already. Just very quickly, so we now know, after August of last year, that neutron star binary can emit electromagnetic radiation at all frequency. So you can get the host galaxy, and that gives you the redshift, or maybe you can get it from the GRB itself. Apparently, we cannot get it from the kilonova due to line smearing. So that is why this method is very attractive. It's very simple. Gravitational-wave gives you the distance. The host gives you the redshift. The challenges are, or were, before our detection, people were very worried about the fact that GRBs are beamed. Back then, we didn't know how luminous everything else was going to be. And if the GRB is beamed, unless you're very lucky, you're going to miss it. But now we know that these systems emit light at a very large angle, pretty brightly, so we can detect them even if the GRB is not pointing at us. The other challenge is that typically gravitational wave sky maps are much larger than the typical field of view of your telescope. We have heard this earlier today. But these also will get better as we get more and more detectors. Right now we are on the tens of square degrees, kind of ballpark number. All right, so before the detection, people have looked at the prospects of measuring the Hubble constant with this method, with the counterpart method, as early as 2013. And what people found back then, assuming n joint detection, you can measure in a cumulative way H0, and they found that the statistical uncertainty could be on the order of a few percent given 10-ish joint detection. But back then, this number seemed extremely optimistic because of the GRB beaming problem I told you before. Other people have looked at the prospects for the next generation of detectors, which, as I told you, will be much more sensitive. So you get more events and you can see them farther away. So these people, in particular, Satyaprakash, looked at this Einstein telescope detector. They assumed that one neutron star every 1,000 will come with a counterpart, hence with a redshift. And now we know that this number probably is pessimistic. And this gives you over 3 years, 1,000 joint detections, EM, gravitational wave. And what they have done, they assume that by then H0 will be known, and they focus on the omegas and the dark energy parameters, and those are the kind of uncertainty they got at 1 sigma. And if you can correct perfectly by weak lensing, these numbers actually get even smaller. All right. The statistical approach, as I told you, you just count all the galaxies, just because you don't have a counterpart, so you don't know which one is the real one. You just get all of them. And the true host will give you the true cosmology. Everything else will act as noise. And as you get more and more events, the noise will average out, and the true value will prevail. The challenge is that requires a lot of sources. And more importantly, probably, it's very dependent on you being confident that your galaxy catalog is complete. This kind of method can be hit hard by galaxy catalog incompleteness. Still, people have looked at the prospects. I have a cartoon that won't show here probably, so I'll show you later if people want to give you the idea. But I'll give you the numbers right now. So the post has looked at this method, and he has shown that you can measure with the statistical approach H0 at a 15% uncertainty. This is 95% confidence level. Now it's not 1 sigma. The literature is not uniform, unfortunately. With the 10 binary neutron star. This was with 3 detectors, HLV, LIGO, and Virgo. Of course, the uncertainty gets better if you have more detectors or if you wait longer, of course. And with the second generation, so with advanced LIGO, with this method, the omegas are not measurable. With 50 sources, you still don't get any information. And the also did not consider dark energy in this problem. And I want to say also that this method has not been yet seriously applied to the next generation of detectors. That will have to happen. All right, that was true, until a year and a half ago. Then this happened. Since the first speaker shared some personal story, I will share also some of mine. I got this circular that tells you we got something. This is the false alarm. These are the masses. I was at NICEF. There are some people from NICEF here in Amsterdam. And so we jumped into a teleconference, got this picture 39 minutes after the trigger time. I think, as far as I know, it's the closest picture to the event of anyone involved. We're still in the teleconference where things were discussed. Then this happened, of course. We got a PRL paper out. And this also happened. We destroyed the PRL server, which is really telling you that, tells you have done something which is important. So basically, PRL started putting the paper on Twitter. That was the most reliable way they found. All right. So I will not spend time on this because the first talk was already about all the electromagnetic counterpart that we found and all the papers and the bands and so on and so forth. What I want to talk about next is what we learn from this particular event when it comes to the Hubble constant. So the money plot of the paper that we published on Nature is this one. In this plot, you are seeing on the x-axis H0. This is, you can probably read, this is 70, okay? And on the y-axis, you have just the probability distribution. It's a PDF, okay? The blue distribution is the one coming from LIGO, so it's a posterior distribution given this one event. And here you find the 1 sigma and 2 sigma, I believe. And the green and orange are the measurements from Planck and SHOES. Now, of course, with one event, we are consistent with everybody. Everybody's happy. And I will tell you later how we can make this better. So what I want to point out, in reference to what I mentioned earlier about measuring the distance and the fact that the distance is correlated with the inclination angle, is that if you calculate the 1 sigma uncertainty of the LIGO measurement, it was roughly 14%. Okay. Of this 14%, 11% came from the LIGO uncertainty on the luminosity distance, and everything else came from uncertainty on the M side, like peculiar velocity of the host galaxy with respect to the Hubble flow. So the gravitational wave luminosity distance is really what has and will, in the next few years, dominate the error budget of measuring the Hubble constant. And I also want to show a different version of this plot. This is a 1D posterior. You can also plot a 2D posterior of Hubble constant versus the cosine of the inclination angle. Again, to make the point and stress the point I made earlier, the inclination angle will be extremely correlated with the distance and hence with the Hubble constant. Okay, so you can see that the main reason why our posterior is so broad and the main reason why it's skewed on the right, the battery died, is that the inclination angle has a bound at 0. All right, I cannot change, or I still can change slides. So how do we get this better in the next few years? The easiest way you can think of is I'll just wait. I will get more and more neutron star binaries, of course. I can add them. I should eventually win like 1 over the square root of n. And this is what these people have looked at, Chen et al. And I'll move there so I can point. So in the top panel, you see on the x-axis, you cannot read it, neither can I, the projection of the LIGO sensitivity. Maybe this is better. You can see the year. This is 2019, 2023, 2026. So here you're adding better sensitivity and more detectors. And the top plot panel gives you the number of detection you're making. This is 100. Okay. By the way, there is a pretty large uncertainty here. This comes from, thank you. It comes from the uncertainty on the rates. We have heard about this earlier today. And most importantly, on the bottom panel, you see the projection of the uncertainty, the relative uncertainty on H0 as a function of time. And the point here is that, say, in 5 years, 2023, we can have a 1 sigma uncertainty on the order of 1 or 2%. Okay, this can be much worse or much large or much better depending on the actual astrophysical rate of binary neutron star that we don't know yet. We will know, hopefully we'll know more in 1 year or so. As I said, you can still measure the H0 in absence of counterpart. This plot assumes that all the BNS come with a redshift measurements because you got the galaxy. What if you don't? If you don't, you can go with the statistical method. I have this one. Okay. Okay, I've redundant number of pointers, but now I cannot change slides with that. I need to change slides. Oh, I can do with this. Okay. Right. So if you don't have the galaxy, you can do the statistical method. It will be intrinsically worse, as I told you, because there are more galaxies that can be the potential host. These dashed lines here give you the evolution of the uncertainty on H0 as a function of time. If you use this other method for neutron star binary in blue, and for black holes, because you can use it also for black holes, right? And what you see is that in 5 years, if most BNS come without host, your uncertainty will be more on the order of 10-ish% rather than on the order of a couple of percent. Okay, so this kind of bracket tells you what you can expect from us using this method in the next few years, between a few to maybe 10%. All right. Oh, this is inversely oriented. What else can we do to do better? We can try to use other sources. So far, we have focused only on neutron star binaries for obvious reasons. Now, as I told you earlier, the bottleneck when you want to do this Hubble constant measurement, it's how well you can measure the distance. And I told you that is degenerated with inclination angle. So is there any system for which we can measure the distance inclination angle better than neutron star binary? And the answer is yes. The answer is neutron star black hole. Now I'll show you the same cartoon I showed you earlier, but I'm replacing one of the neutron star with a black hole. I gave the black hole a spin, as most black holes are expected to have spins, even large spins. What's going to happen is that unless the spin of the black hole is exactly oriented with the orbit, you will have a total angular momentum. So L, the orbit, will start proceed around J. And this means that the orbital plane will start wobbling around. So from our point of view, here at Earth, we get more or less gravitational wave energy as a function of time, which basically means that the gravitational wave amplitude will receive a modulation, okay, which is shown in this kind of waveform. That's a waveform for a neutron star black hole binary, where the black hole has a spin of 0.7, I believe, and 45 degrees inclination with L. And as you can see, this is just windowing. Don't worry about this. You can see the amplitude is modulated. And now this modulation breaks or strongly reduces the degeneracy between D and inclination angle, which means we can measure the inclination angle for neutron star black hole better. Furthermore, neutron star black holes are also expected to be electromagnetic bright because the black hole should eventually disrupt the neutron star, so you have a lot of material going around. Although the details of this, I should say, are not really clearly understood yet. All right, so what happens? What happens is that you have very many attractive things about neutron star black hole binaries. They will produce electromagnetic radiation. They will give you a better distance measurements due to spin precession. And by the way, this is shown numerically in this plot from a paper we published on PRL a couple of months ago. What I'm showing here on the x-axis is the true inclination angle. 0 is face on, pi/2 is edge on, and 1/8 is face off, so L going away from you. So that's the true value. And on the y-axis, you have the relative uncertainty on measuring the distance for that particular system. You have different curves. I won't go through all of them. What I want to focus only on the black one, which is the uncertainty you will get for a neutron star binary. The reason why there is this structure, it's actually very interesting, but it takes 5 minutes only to explain it, so we can talk about it later if you want. And everything else is uncertainty you would get for a neutron star black hole with different value of spin orientation and magnitude at the same scale position with the same signal-to-noise ratio. So it's really an apple-to-apple comparison. And you can see that your distance uncertainty once you have a neutron star black hole is typically a factor of few to many better than what you would get with a neutron star with equivalent signal-to-noise ratio. So this numerically makes the point I made conceptually. A neutron star black hole will give you a better distance uncertainty and hence a better Hubble constant constraint than a neutron star binary. And I can see them further away, which is also nice because if they are farther away, the Hubble flow velocity there is larger, so the uncertainty in the peculiar velocity matters percentually less. So it's also very nice. So this is all good. What is the downside? The downside is that, as far as we know, there are way fewer neutron star black hole binary than neutron star binaries in the universe. So which of these factors win eventually was really why I started working on this paper. And the bottom line is this kind of plot here, which I'll take a second to explain it because it has a lot of information. Of course, we don't know the real rate of neutron star black hole. We don't even know the real rate of neutron star binaries. So as figure of merit, we have used the ratio of the true rates of neutron star binaries over neutron star black hole, which is unknown, so you can pick whatever you believe. And on the y-axis, we have the cumulative uncertainty given n detection on the H naught for neutron star binary divided by neutron star black hole. So basically, if in this plot you are above this line, it means that neutron star black hole are giving you a better constraint than neutron star binaries. And you can, depending on which value of spins for the black hole you are considering, you can see at which relative rate that happens, at which relative rate neutron star black hole start being more interested in neutron star binaries. And the red band here, it's the current relative ratio of the rates that we get from astrophysicists, which is very broad. But the bottom line is that even in the worst assumption, in the worst case scenario, you can do better with the neutron star black hole. Sorry, this should be neutron star black hole, no binary black hole, I apologize. You can still do better with neutron star black hole, even if there is only one of them for 10 neutron star binaries, okay? And if the spins are larger or more misaligned, even if you have one every 50, you can still do better with neutron star black hole. Okay, so this is to say that these other sources may also contribute significantly to measuring the Hubble constant. What else can we do? We can try to use some other information than the redshift from the electromagnetic side. Again, the bottleneck here is the degeneracy between inclination angle and distance. So if I can know something about the inclination angle by other means, the gravitational wave, I can fold in that in my analysis as a prior, and that will reduce the uncertainty for the distance. That's what we have looked at with this bunch of friends in this paper. We have considered two possibilities. The case where the electromagnetic counterpart and the modeling that comes with can tell us something about what the true value of the inclination angle or viewing angle is, with some uncertainty. And we have looked at how much better your uncertainty on the luminosity distance, this is the uncertainty in luminosity distance in percent, this is 5, 10, 15, 20, gets as you assume you know more and more about the inclination angle from the EM side. So this is a cumulative distribution. The blue curve is in case you don't know anything. Okay, so you don't know you don't have any information about the inclination angle from the EM side. You have to do everything by yourself with gravitational wave. Worst case scenario, of course. In that case, for 50% of your sources, BNS, the uncertainty will be on the order of 15% on the luminosity distance, and that will translate immediately on similar uncertainty on H naught. Now, if you assume that you start knowing more and more, so these are all cumulative functions that give you the uncertainty as your prior information on the viewing angle. It's a Gaussian with a width of 2 degrees, 5 degrees, and so on and so forth, until you assume that it's perfectly known, which of course is very unrealistic. And you can see that you have roughly a factor of 3 that you can gain for each event on the uncertainty in the luminosity distance as you gain more and more information from the M side on the inclination angle. So this is to say that in the next few years, as hopefully people that do electromagnetic modeling of cocoon or jets or whatever start believing more on their models and they can tell us something about the inclination angle from the N side, we can fold in that information and get a better constraint on H naught. The other case we looked at, this is a Gaussian posterior, prior. The other case we looked at is just an upper limit on the inclination angle that could come if you see the jet break, okay? If you see the jet break, that gives you an idea of the maximum inclination angle because it's the size of the cone. So in this plot, you see for different values of the true inclination angle and for different values of the half opening angle of the GRB that I'm assuming we can get from the N counterpart, how well or how much better your distance uncertainty gets. Okay. Again, same message. If you get more information, if your GRB is very beamed and you can measure that angle, you can fold it. You can fold that as a prior in gravitational wave analysis, and your distance uncertainty can get a factor of 2-ish better. All right. All of this was true and relevant for systems for which there is at least one neutron star. 1 in the case of a neutron star black hole, or 2 in the case of a binary neutron star. What about binary black hole? It kind of sucks that we cannot do anything with them because they're going to be the most common source that LIGO will detect in the next many years. And as far as we know, they're non-luminous, so we cannot use anything that relies on EN counterpart. They don't have any tidal deformability, so I cannot use anything that relies on tides. The only method that will work for these systems is really the statistical method that I mentioned earlier. You get the 3D uncertainty volume from LIGO, Virgo, Cagra, and so on and so forth. You follow up all of the galaxies, you measure all the redshift, and so on and so forth. That's going to be worse than the results I showed you earlier for neutron star binary for a very important reason. Binary black hole are heavier, which means we can see them farther away, and our uncertainty also gets larger. Okay, and also binary black holes are shorter, as Chang-Li shown earlier, and they last in our LIGO band less than a second. So measuring the sky position, it's much harder. We're not talking of 10 square degree, we're talking maybe of tens of square degrees. So the number of galaxies that you have to follow up now is increasing, and hence the power of this method decreases. That's one problem. The other problem with them being farther away is that you probably are less and less sure that your galaxy catalog are complete at that point. So this is to say that there is still a lot of work that is required to be confident that this method, the statistical method, will work without any significant biases for binary black holes. However, what I personally looked at, it's a kind of best case scenario, which, however, we know will happen, it's just a matter of time, is if I focus, instead of advanced LIGO, I focus on this future detector I mentioned earlier. I told you they are a factor of 10 better in sensitivity. This means that if I have one of these future detectors online, Here you have several of them, but don't worry about it. That's not important. If I have a binary black hole nearby, like 15914, like the first detection, so I'm not making up anything unrealistic here. I'm considering an event like the one we have already detected. If we have these future detectors online with this source, well, the signal-to-noise ratio will be on the order of thousands or hundreds, depending on the facility. And with this signal-to-noise ratio, the uncertainty on your sky position and distance measurements for this binary black hole would be so small, you can see the number here, that on average, on that 3D volume, there is only one galaxy, okay? So although the binary black hole is not luminous per se, it's localized so precisely that there is only one galaxy that is compatible, of course, on average, with that event. So at that point, the statistical method collapses in a kind of delta measurements where you know the redshift from the one galaxy. So you are limited, assuming that you have the host, you are limited by how well you can measure the luminosity distance for this kind of very loud event. And if you look at this table, or you believe me, it's 1%. Okay? So with these future detectors, for nearby events, a single binary black hole will give you, from our side, an uncertainty on H0 on the order of 1%. And now, since we have on the order of, you can do the math, we will have on the order of hundreds event with this signal-to-noise ratio per year. You do the 1/√n improvement, you get, with 1 year of future detector, you get H0 at 0.1%. Now, at this point, you may all be very happy, but there is a big yellow caveat here. The caveats are systematics, okay? And that's my last slide. I hope I'm doing well with time. What are our systematic? Because we all know, systematic we get from the electromagnetic side. I said we don't share any of your systematic, which is true. I don't use the cosmic ladder, I don't use standard ruler. But that doesn't mean we don't have our own systematics. The main ones I think we should keep in mind are two. One is calibration of the instrument, of LIGO or whatever comes after LIGO. Of course, what LIGO gives you is a voltage, okay, in a photodetector. You need to convert voltage in delta L over L in strain. That comes with a loop that you need to calibrate. This calibration, as all measurements, is uncertain. Right now, our uncertainty on the calibration of LIGO for the amplitude of this strain, which is what we care about for distance and hence H0, is on the order of 5%. Okay, so this number is probably okay-ish for the next couple of years, and it can get better. But clearly, this is not enough for what comes after LIGO. So a lot of work is going on to improve these measurements. I want to tell you, it's not trivial, because eventually what we are limited by is the calibration of the calibrators. Because to calibrate LIGO, we use a laser, and the laser is calibrated by NIST, the standard Institute of Calibration in the US, or measuring in the US, and they believe their own laser at 1%, or actually 0.86. So that is the threshold we are seeing right now of how well we can do, unless we come up with something else. But that's not 0.8% is not a problem for many years. The next one is waveforms. To give you an idea, for the events we detected in the first science run, take 15914, we use more than one waveform family to measure all the parameters. And for example, for the two families that we use in the published paper, the uncertainty on the distance for 15914 varied by roughly 10%. Okay, so one posterior was roughly 10% larger, although they were still centered at the same position. Okay, now I'm not very worried about this because waveform can and will improve. Actually, as a matter of fact, this is already improved since 2015. Has already improved. All right, I'll stop here with my conclusions, which is that theoretically and practically very soon, we can measure all the cosmological parameters with gravitational waves. Now, with advanced detector, we're going to have to stick to H0, very likely. We, at this point, believe that with a few tens of binary neutron star, with the M counterpart, which means 5-year-ish, we can give you a couple of % measurement. And neutron star black holes, as we start detecting them, may bring this number even down. And for other cosmological parameters, omegas and Ws will take longer, will take next generation of gravitational wave detectors. And the bottom line, for which I think this talk is relevant for you, is that our uncertainties might not be better than what you can get or you will get in 5 years or in 10 years with other probes, but they have, in my opinion, very attractive feature that we do not have any of your systematics, so hopefully will help arbitrate the tension. Thank you.
Got a question there?
Thank you. To estimate H0 in a model-independent way, you need these sources to be very close to us. I think in one of the cases which you showed for the future measurements, I think the distance is something like a 500 megaparsec, right? Which already at that distance, for doing precision measurements of the H0, you need to know your cosmology.
Yeah,
right?
you can. So you can.
How?
Well, you measure everything. Basically, you start. Let's see. You start from the whole.
No, I understand that you get DL with a 1% precision. Let's assume that you get DL with 1% precision. But if you are beyond redshift of 0.05, it's like, you know, what you showed, like a few hundred megaparsec, then, you know, you have the small h inside the integral, right? Yeah. Which is model dependent then. You know, you need to know the components. Unless your source is really near to us, which, you know, it would be completely independent of the cosmology. For very high precision, we still, you know, need to know the cosmology. Okay. So what would be the probability of these binary neutron stars at a very small distances, let's say like 100 megaparsec? Do you expect that we observe anything in such distances?
Oh, yeah, yeah. So let's see if I have it. Which way am I going? I'm going back? Yeah. So the plot at the beginning with the horizons, let's see, showed what you can expect from LIGO in terms of distance as time evolves. And okay, the plot is cut here, but so 0.1, which is 200 megaparsec-ish, it's as far as we can see. Okay, so those will be the most common because far away there is more volume, of course, but they will also be the weakest we see, right? Now, if this plot were not cut here, you would see this band here, which is where you can see, you know, 10%. So 90% of the source is here, and 50% below the light blue, you will see that they're much closer, okay? So they're on the order of, you know, 0.05-ish, okay? So I think the typical detection as advanced LIGO progresses will be at 0.09, 0.1, but the most useful, which are the loudest, will be, of course, much closer. So, you know, between 50, say, and 100 megaparsec, something like this. Thank you.